Alright, so I have a quadcopter here. It has a Teensy 3.2 and an IMU with a carbon fiber frame. It's a 180 size quad. So I'm doing a model-based controller. So in order to do the model, I had to make a model of it to get the moments of inertia accurate. So here I have the model. Can check the properties. As you can see, it gives me the moments of inertia. Using that, I made a MATLAB script which accounts for moments of inertia. Also, time constant of the motor, which I have a test rig for that. I can show you a version of that. So here's the response to the time constant. These fuzzy values are discrete effects I didn't really care to take account for because I was able to get the time constant by filtering the data. Okay, so now that I have the moments of inertia and the time constant motor, I pretty much have everything I need for the quadcopter in terms of physical properties and actuator dynamics. So I specify a sampling time, bandwidth of the system, phase margin, and then I also specify things like integral control, which I'm having a little issue with because I have integral windup, so I need to separate it from the controller and then limit the integral windup. Yeah, that's the next thing. Shouldn't take too long to do. And then account for additional things like throw in some roll off, account for the zero to hold, pre-warp the frequency, apply gain correction, which I found was handy. I'm also going to do an attitude control. So right now this is just rate control. So let's see what we get. It's going to show me attitude plots too, but don't mind that. It takes a little bit to run. So and I'm just using this script to just do the rate control. I haven't messed with the attitude control too much yet in terms of actually applying it. Okay, so here we see the continuous domain control. Okay, we see settling time about 0.03 seconds for rate, which is pretty good. And here is the control signal that's sent, and here's the actual followed command. In this case, this command is actually a net torque about an axis. So this is the P rate, or your first axis rate, and so you have to send this torque signal to the motors, which is basically just take that torque value divided by 4, and then also divided by the arm length, which is in my case 60 centimeters. So I'm sorry, 6 centimeters. Anyway, so I have a discrete version because I have a computer, and sure enough, it looks very similar after applying all the tricks that I've learned. It's very similar, okay? And so what I want to show you next is it actually flying. So I'll do that now. Okay, so you saw it fly. One of the things I wanted to mention, the difficulty I had was I would design a control law, and even though it looked good in simulation, because the motors have an output maximum, a certain thrust, and because the sensors have a certain amount of vibration they can take before they just get too noisy, I had to limit the bandwidth, half the bandwidth I really wanted. It's not going to be a big deal in the end, but in this case, you know, maybe if I dampen the sensor more, then it might help a bit. But yeah, up next we'll do a cascade attitude control, and then after that we'll move on to this guy here for more advanced things. All right, thank you.